monitoring.
We have to go on. Thank you, Rob. Our next speaker is Dallas Masters, and Dallas will talk about Muon space constellation for GNSS-based remote sensing.
Well, I'm almost tempted to cede my time just so we can continue that discussion. And actually, I'm going to start by talking about an anecdote, actually, because of the anecdotes that were given yesterday. Back in 2020, Sean Healy and I worked on a project together, and I don't think people remember it much, but actually Vu showed a picture of it today. It was when Spire gave all of its occultations for about a 5-month period to the world to assimilate. And there was a large jump in the FSOI score at ECMWF. That was an interesting example of commercial working really well with the government agencies. What you didn't realize that happened during that time was it took us 5 weeks to go from no RO going in the ECMWF model to it being operational. And I remember Sean telling me that he had to go to the highest level of ECMWF to get this approved, and that if it didn't work, we probably both would be out of a job the next day. And the day that we decided to do this, he said, okay, tomorrow morning we're going to wake up and either the forecasts are going to be great or the forecasts are going to be broken. And we did that within 5 weeks. So it's amazing that we spend so much time, years evaluating data. We can go from 5 weeks to having no profiles going into the ECMWF model to having 7,000 profiles. And that was like a mini Romex that happened at that time. So I think we should think about how fast we're doing things, because there's definitely examples in the past where we've moved really quickly and seen really great impact. So now I'll switch back to talking about Muon. So I'm going to talk about MuonSpace, which is a company that I joined a couple of years ago. We're moving very fast. MuonSpace is building small satellites. These are not CubeSats. You can see this is about a satellite that's on the order of about 1 meter in size in the large dimension. We are building these satellites for commercial and government agency constellations, delivering Earth intelligence. My particular group is building GNSS-based remote sensing for these satellites, and we're applying this for surface remote sensing as well as space weather applications. I've built this team of signal opportunity experts. You can see a lot of them are denoted as having some expertise in GNSS-RO as well as tech measurements. The people that have the little asterisks next to them, these are people that have expertise in GNSS-R, GNSS-RO, and GNSS-based remote sensing. We're collaborating with the University of Michigan and Ohio State University to build some of the first satellites. You'll see that in the next couple of slides. And we're focusing on products that we can rapidly develop with machine learning algorithm techniques. And you also see this as well. You can see that I've recruited people like Steve Lowe from JPL to work on this. Clara Chu came from UCAR and is an expert in soil moisture retrieval algorithms, as well as people like Linus Tan, who was the payload lead developer at Spire previously. So we are interested in developing Earth observations for small satellite constellations. GNSS-based remote sensing is actually a very good technique for doing this because it's a very small payload, obviously. This is a type of cartoon that I've shamelessly stolen from Spire, but it does explain a lot of the remote sensing techniques that we can do with this GNSS-based remote sensing. Obviously, we're looking at ionospheric measurements. Rate occultation measurements are possible. We're not doing those right now. And then as well, the GNSS-R or reflectometry measurements. The ones that I've highlighted here that are circled in the dashed lines are the ones that are actually under contract right now from the U.S. Air Force through its evaluation program. So if you recall, the Air Force has a commercial weather data pilot program. It kind of morphed into different areas in the past, but we actually applied for that. And the Air Force is evaluating our tech measurements, as well as our surface soil moisture measurements and our ocean wind speed measurements from a satellite that I'm going to talk about, MuSat-2. So MuSat-2 is our second satellite at Muon. We launched our first satellite in June of 2023. We've launched the second satellite in March of this year. This satellite is basically the equivalent of a Cygnus satellite, if you're familiar with the Cygnus satellite mission. It flies a 2x3 antenna you can see on the bottom of let's see if I can figure this out. Right, I can. So this is basically a Cygnus type of reflectometry antenna. The difference between this antenna and a Cygnus antenna is this is a polarimetric antenna. So this does LHCP and RHCP. This is almost the equivalent of the Hydro GNSS mission that ESA is going to fly next year. We also have two Zenith antennas. One of the Zenith antennas is attached to a Novatel receiver. The other Zenith antenna is attached to our homegrown receiver that we've designed at Muon. Our receiver is based upon state-of-the-art SDR technology. It's a multi-channel receiver, so we can have multiple antennas attached to it in the future as well. It's wideband, so we can do L1, L2, L5 reflections. So this is basically the equivalent of the Hydro GNSS mission, but flying right now. And we can also track all signals in view: GPS, Galileo, Beidou, and QZSS. We're currently only tracking GPS, but we are adding Galileo and the other constellations very soon. The Air Force was interested in topside tech. We don't have a space weather antenna on this, as you can see, but they were interested in topside tech. So this is basically generating tech measurements with the Novatel receiver through that antenna on the top. This is a picture of the satellite built over here on the left-hand side. You can see those dual polarimetric antennas. I'll mention that these antennas were actually designed under a NASA ESTO IAP by the University of Michigan and Ohio State University. So this is making dual polarimetric measurements. If you're familiar with GNSS reflectometry, polarimetric measurements are interesting over the land surfaces, where we would potentially be able to correct for surface roughness effects and vegetation, not necessarily over the ocean. It was launched in March of 2024, and it's put into a polar orbit. So this gives us polar measurement or full global measurements compared to the Cygnus measurements as well. And we're currently collecting, like I said, the dual polarimetric measurements. We started out doing only LHCP, but we've added the RHCP measurements as well. The spacecraft, I'm happy to report, is healthy. It has been producing measurements since about May. We launched in March and went through a checkout and commissioning phase. We're currently tracking about 6 to 7 simultaneous GPS L1CA dual pole reflections. We produce 2 Hertz measurements, and this is so that we can have a reduced spatial resolution over the land surfaces. We also have a different DDM resolution than Cygnus. This is about a 1/8 chip and a 250 Hertz Doppler DDM, so it's finer measurements than Cygnus as well. And then the Novatel receiver is also operating in this mode to collect pseudo-range and phase measurements that we turn into tech observations on the top side. And so those measurements are from all constellations. And so there's quite a few measurements of tech being made on the top side. Initial product status, we're generating right now ocean surface winds and soil moisture measurements and those tech measurements from this satellite and sending them to the Air Force. This is a first track of the measurements from May 22nd. This is kind of like our first light data, so I like to show this. We were collecting data over Antarctica, and this is basically a track of a reflection as we left Antarctica and started out going over the Southern Ocean. What you see in the time series plot on the right is basically just the reflectivity values that we see as a function of time here. And the peaks in the reflectivity are showing you where there's actually openings in the sea ice. So this is a very reflective ocean surface, so you get a very strong peak. And we also correlated this with measurements from synthetic aperture radar, as well as optical measurements showing where these leads were in the sea ice. You can also see that it kind of goes out over the ocean, the ice edge drops off. This is exactly what you expect in terms of the signal to noise ratio. And you can also see a little bit later on this kind of wind roughened ocean surface changes, and there's potentially even a calmer ocean surface. One of the other things that we did right at the very beginning was to compare the signal to noise ratios that we're measuring over land surfaces to those of Cygnus. So what you see in this plot on the right-hand side, if you squint, and this is the point, if you squint, you can see our track. Because it's so faint, it's because we're actually matching the signal to noise ratio measurements over this land surface that Cygnus also measured. And so the background of this plot is actually the Cygnus SNR measured over many tracks of Cygnus data and our MuSat-2 plot over the top of it. And so it's a good example of the fact that our measurements are agreeing very well with Cygnus. Before we even launched MuSat-2, we started developing the soil moisture and ocean wind products using a machine learning algorithm technique. And so we built a framework here, which is very adaptable. I was talking to someone about the fact that if freeze-thaw measurements over soil moisture or sea ice measurements are interesting, we can actually adapt this machine learning technique to attack new applications very quickly. And so we've already done some things with freeze-thaw as well by using this technique. So we built this for Cygnus data, and we now have operational Cygnus products being generated. This is an example of Cygnus soil moisture data that we generate compared to SMAP. SMAP is on the bottom. Our Cygnus soil moisture is on the top. What you see is actually two seasonal maps here. On the top is actually a wintertime map, and on the bottom is a kind of summertime map. What I'll highlight on the right-hand side of the slide over here, if I can do this correctly, is a difference in the soil moisture resolution from GNSS-R versus SMAP. And this is, I think, what is important about understanding the potential for soil moisture measurements from GNSS-R. GNSS-R is fundamentally driven by the surface roughness effects of the land surface in terms of its spatial footprint. So if we are over a pretty smooth surface, our spatial footprint is on the order of 1 kilometer to 3 kilometers. And it's very hard to tell you exactly what it is, because it's dependent on the surface roughness, but you can see the effects of the surface roughness, or I'm sorry, the spatial resolution compared to SMAP in these plots. This is our data gridded at 9 kilometers compared to SMAP data gridded at 9 kilometers. And so this is where there's a lot of potential here for soil moisture measurements from GNSS-R. We also compared our data to in situ sites. We have comparable performance as well to SMAP type measurements. But remember, the difference in cost of SMAP to one of these types of GNSS reflectometry missions is a few orders of magnitude. SMAP is $1 billion mission. This is a commercial satellite that's producing, or this is Cygnus data. So Cygnus data was basically 150 million. And that's 8 satellites producing that data. These are data that we generated ourselves from our current satellite. So I'm switching over now to show you the early results from MuSat-2. So these are data that we're collecting from MuSat-2. This basically, like I said, is our version of Cygnus. These are LHCP only measurements. We started making these measurements in May 27th. This goes through August 19th. And you can see that we are starting to make measurements of soil moisture that are equivalent to Cygnus as well. This is actually a very temporary empirical method of producing soil moisture because we don't have that much data to train the machine learning model. I also want to go back here. Notice the RFI that we are flagging out here. We're doing a very conservative flagging and throwing out a lot of data, but this is something that I think the community should be aware of, that RFI is really affecting these satellite missions, both RO and GNSS-R. I would be very careful to build RO missions with L5 frequencies only in the future, because L5 is really going to be experiencing a lot of RFI. This is our retrieval of ocean wind speeds as well from MuSat-2. So you can see this is basically producing ocean wind speeds with our ML model that we've trained with Cygnus data. Now we're applying it to MuSat-2 data. And so we're going to be continuing to improve this model as we keep collecting more data. And then finally, this is just a first peek. But remember, this is a mission that is like HydroGNSS. It's trying to do dual polarimetric measurements. And so we can look at the ratio of the LHCP to RHCP reflections. This is basically a track of one of those polarimetric ratios that's been superimposed on a map of Afghanistan. And what you can see is that there's definitely changes in these polarimetric ratios with respect to either the surface cover type, trees and forested areas, as well as surface roughness. And this is exactly what we expect. And this is where we can potentially correct some of our soil moisture measurements with this dual polarimetric type of data. We're also collecting tech measurements. As I said, this is sort of a byproduct. It's topside only, so it's not that interesting, but we are converting the conventional Novatel receiver phase and pseudo-range observations into tech. Again, these are being made with all of the observations that a typical receiver would do. So this is a lot of observations per day, on the order of 500 tracks a day from these different constellations. So this includes Beidou, GPS, GLONASS, and Galileo. And then finally, I'll end as well talking about the plan for the next satellites. So what you see on the left-hand side is the satellite that we launched in June. It does not have June 2023. It's the first satellite that Muon launched. It does not have a payload. The second satellite is the MuSat-2 that had the GNSS-R payload that is equivalent to Cygnus and the HydroGNSS mission. And then we have 2 more satellites that are actually being built right now, MuSat-3 and MuSat-4. MuSat-3 is a commercial satellite that we are putting the GNSS-R payload on. It's actually equivalent to the MuSat-2. So in 2025, there will be 2 of these dual polarimetric Cygnus equivalent type of missions flying. And then MuSat-4 is the one that I'm very interested in. MuSat-4 is where we're actually moving towards a high gain beamformed antenna. And this is to try to improve the surface wind retrievals in hurricanes that are suffering from just a lack of signal to noise and low gain from these antennas that are kind of equivalent to Cygnus. This antenna will be on the order of 19 dBi gain, and we intend to beamform as well with that antenna. It's not shown in here. Probably in my next presentation, I'll have the ability to show that type of antenna. And as well, that it will potentially help us to retrieve soil moisture in canopied regions as well. So in conclusion, MuonSpace is a new company. We're focusing on GNSSR technology and the GNSS in general. We've launched our first satellite, MuSat-2, that's producing these measurements. We're under contract with the Air Force to produce soil moisture, ocean winds, and tech. Doing this with machine learning algorithms to move really quickly. We'll be launching 2 more satellites in 2025 that'll also produce these measurements. And I'll end as well by saying that we're looking for collaborators to work with our data. One of the things about a small satellite company is that we produce lots of data, but we don't always have time to look at all of it. Just like I mentioned about the dual polarimetric data, we have a lot of polarimetric data that we have just barely scratched the surface looking at. So we are looking for people to help us, whether it's an academic institution or government institutions that would like to work with us. So please get in touch with me in the future, and we can potentially collaborate. Thanks.
Thank you. Are there any questions?
Yeah, really quick one. So your MuSat-4 with beamforming high gain antenna, what kind of wind speeds do you expect to be able to retrieve the maximum?
Okay, so that antenna was actually designed based upon the work of Chris Ruff and his graduate student who looked at the saturation for Cygnus measurements and attempting to try to retrieve hurricane wind speeds that were greater than Cat 1 type of wind speeds that they currently can. So that is based upon his work of estimating that we need about a 19 or 20 dBi antenna to achieve this category 4 type of wind speeds, category 4 and 5. So it remains to be seen.
Rick?
Hello? Okay. It seems like there's no doubt that you can produce interesting scientific data to service on this, but I'm curious about the business model, because radio occultation unquestionably, undeniably shows a huge positive impact on NWP, and yet it's still a struggle to get enough data sold, is my understanding, to make this a profitable business. And the impact of these service data will undoubtedly be positive, but it will take some time to show that. And it's, in my opinion, unlikely to ever show the degree of impact that radio occultation already does. And we're already having trouble selling enough radio occultation data. So how do you square all this?
Great question. A couple things. We did not go into this business model not understanding that. And one of the things about RO is sold to numerical weather prediction services. And basically then it stops. This is soil moisture. This has other applications besides numerical weather prediction. So it's a very good example of a product that doesn't stop with selling it to the NWP centers. This is potentially a product that can actually impact agriculture, insurance, and other areas. So I totally understand what you're saying. And I actually think that we have to look beyond what we just sell to government agencies, but potentially what other commercial entities are interested in. I mentioned the MuSat-3, the commercial company that's paying us to build that satellite. That commercial company is Hydrosat. And Hydrosat is interested in agriculture. And so they have a payload on our satellite that is going to be impacting agricultural applications. Our soil moisture data might also benefit that type of market. And so there's definitely some of these measurements are not going to stop with just NWP use, but potentially have other applications. And I think the other thing you're saying too, Rick, and we've experienced this, is when we ask if the NWP centers are ready to use soil moisture or ocean winds, the response a lot of times is no, we're not ready. We're not going to be ready for 2 years. And so, as I think Chris McCormick said, or somebody else, we're moving much faster than the actual agencies, and that's unfortunate. We would love if the agencies could use the data quickly, but that's just the reality.
Okay, thank you very much. I think we have to move on with the next session, actually. And Julia will come up here and